Welcome everybody. After a bit of summer break, planned summer break due to lack of the space, we are back. And today we will be talking, starting a new module. I don't know how long the module will be, but we hope to fit everything in. And we'll be talking about introduction to templates. But before that, first of all, a massive thank you to Cloudflare and Michael for getting us the space. So this week and the following week, if we behave well, we're here. So thank you very much. Much appreciated. So what else? Massive thank you to our patrons, yes? These people here, basically they pay the money and they allow us to purchase the equipment. What I have now is not ours, but basically we do have some equipment, which obviously helps to run the classes. We hope at some point to get to the position where we can even pay for the space if we can't find a space and so on. But obviously that depends on the sponsors. So we're still looking for a house. However, there is some development. L'Oreal basically passed the name to one of the universities, and they raised the interest to have us in their tech lab. So from September, I'm not sure whether it will be middle or end of the September, we potentially will get a permanent space with them. So we will have the basically once a week chance to go there and run a class, and they're located in Margate. So fingers crossed. I really hope that this will pan out, because as you can see that finding space is not something easy, and it takes lots of time. So rather than working on something to make the classes better, we're relying on our headless chickens to try to get the space. So what we have, I'm sorry about this spelling, I was just rushing. We have introduction to templates, 5 to 6 weeks, hopefully shorter possibly, yeah. Anyway, that was the initial one. We might have to change it depending on the...
We have to cut it out a bit because I think the delay is behind because of we have to unfortunately testing classes. So,
Sadly. And after that, obviously, we'll start in the new course. Obviously, we encourage everybody to continue, and even not in the sense that you will learn on the start something new, but help other people. And by doing this, you will learn as well something new, because the information is sticking in a different way in our heads when we teach somebody. So, what else? I'll just skip this through because pretty much in the room we have everybody already is aware of that. So we have meetings on Tuesday with lecture, and on Thursday where we're trying to run a workshop. But obviously a lot depends, especially for Tuesdays if we have a space. So please do let us know if you're coming for Thursdays, because I had a couple of people who said that in the last moment they messaged me, oh, where is the meeting? The thing is, say like Tuesdays, Thursdays, we need to know who is coming. So somebody, most of the time, Oliver, that he can commit his time, because if nobody's coming, obviously he will make an alternative plans. If anybody needs a license, do let me know, send me an email, message me on Slack, and I will send you 6 months license. Put on the subject CLION license. I'll give you the email my email address if you message me on Slack. Wants to sponsor us, wants to support us, well, there are a couple of ways. The first one obviously is the patrons. For you as a student, if you think what we do is good, you can help us by basically paying a couple of pounds or whatever you feel appropriate. Find us sponsors like the Cloudflare, yes, is basically they offer us a space, we don't have to pay for it. So that's an amazing thing, that's a really big help. Social networks, spread the word about us. And finally, obviously, make sure that Tristan and Oliver are very well looked after. So when we finish the class today, we go to the pub, yes, we might jump on the big wheel and drink from top, let's say. So these guys are well looked after, so they get a couple of pints and maybe some nice food. So that's all from me, pretty much. The last thing which I would like you to do is, can you please make sure that you check our website for updates? Because, you know, I got somebody who messaged me last week, you know, running like headless chicken in Mergate. Where's the class? Sorry, the class has been cancelled. You know, you didn't read the message. So that's all from me. I'm passing now to Tristan, who will tell you way more interesting stuff than I did. Thank you very much. Oh, by the way, if you have a question, switch on the mic and said, because we don't have our recording equipment, is with Ollie. And we need to speak quite loudly so the internal mic will catch it, what we're going to say. Thanks very much.
Just give me a second to change the screens over and I will be with you. Okay, I think we're on.
Thank you, Tom. Thank you as well again to Cloudflare for hosting us in their really cool central London meetup space. You can see the London Eye have the windows at the back. It's awesome. Sorry to you guys, by the way, because I'm going to be sort of hovering between that screen and that screen because you've all decided to sit off to one side for a company. So,
Yes, never mind, I'll manage.
You're all the really hardcore, you guys. You've been here dozens of times before, so you've all seen this slide many times. But if there's anybody watching on YouTube for the first time, wants to join in with what we do, we really encourage everybody to come and join our Slack channel. So head to that URL. Hopefully they fixed it now. You can sign on. So go to that URL, put your email address in. Send you an invitation to come and join the CPD Land Slack. And then you can find our #CPD London Uni chat room in there and talk to all of us, because we're all really lovely and would love to hear from you. All right, so what are we doing? So the next couple of weeks we're going to be talking about templates. Yeah, exactly. We're going to be talking about templates, which are the sort of one of the most powerful, but in some ways slightly most mysterious aspects of C++. You can do astonishing things with templates, but they're not always all that easy to get to grips with. Today, however, we will be focusing, trying to focus on the bits that are quite easy to get to grips with. We'll be looking at what exactly templates are, how we use them, how we write our own simple templates, class templates primarily. So, specifically, we're going to be looking at what templates are, why we like them, why they're a good thing, why they're an awesome addition to the language. As I say, how do we use them, how do we define our own? We're looking at how we write class template member functions, or define them out of class. And then finally, we're going to look at template specializations, how we write those, why we want them, how we write them. So that's what's on the menu for today. I'm not quite sure how many sessions this little module is going to go over, because we are planning to restart in September, so depending on how many sessions we actually manage to run, depends on what we're going to do next week, how rushed we have to be in a sense, but you know, that's for today anyway. Oh yes, by the way, I do have some horrible summer germs, so excuse me if I keep coughing very loudly into the microphone. Alright, so what are templates? What is a template? What do they do? How do we want them? So templates are a C++ language facility that allows us to write code that is generic, reusable, it's type safe, and really amazingly, incredibly efficient. Now, one of the things that allows C++ to be as fast as it is, to be one of the fastest languages out there. And a template, in a sense, is like a blueprint for how to write something in C++. So if we have a class template, it's like a blueprint for how to write a class. So we all know, hopefully by now, how we write classes. A class template isn't a class, but it's a blueprint for a class. If you want to think about the relationships between class templates and classes, it's like the relationship between a cookie cutter and a cookie. Right? Templates are like cookie cutters. They tell us what the shape of the class should be. But they don't actually create a class themselves. Templates in C++ are purely compile time, completely a compile time mechanism. They're a way for the compiler to generate classes and functions, and as we'll see in a minute, aliases and variables. It's a way for the compiler to generate those things for us. Right? There is no runtime anything to do with templates. Right? If you are familiar with generics in Java, for example, that's basically sort of fancy way of doing type erasure that lets you know, adds a bit of type safety, but under the hood in Java it just uses the base object type. C++ is the way the generics system works in C++, that is the template system, is completely different. Because the compiler is actually generating new classes and new functions for you based on these blueprints that we give it, these templates. And it's quite important to understand the difference between a class and a class template, and the difference between a function and a function template. Because sometimes we're quite slack with language and we refer to, we sort of mix these things up, but in terms of the actual language, they're really quite different things. So, as I say, I didn't come up with the analogy. I heard it in a fantastic talk by Walter Brown. He came up with this analogy of the cookies and cookie cutters. So a template is like a cookie cutter, right? You wouldn't mix up a cookie and a cookie cutter, right? They're completely different things. And class templates and classes, function templates and functions are different things. We can generate a class from a class template, but we can't. That's the only way in which we can use a class template. Right? A class template does not define any new types by itself. So a bit of terminology. When we use our cookie cutter and we create a new cookie from it, we refer to that as a template instantiation. If you're into Rust, they use the term monomorphization, which I think they just use to sound posh. But you'll start, well, it sort of makes sense because you're starting with something that's polymorphic, works on many types, and you create a version for a specific type. It's monomorphization to a single form. But when we instantiate a template, a class template, let's say, with particular template arguments, and the compiler then goes away and it uses this cookie cutter to create a new cookie, a new class for us, instantiates the template, specialized just for those arguments that we give it. In order to do this, the compiler needs to have the full blueprints, the full plans available. It needs to know all of the code that it has to generate for this new class. And this means that generally, by and large, our template code has to live in header files. This is one of the things, unfortunately, can make C++ slow to compile sometimes, is because all of the template code has to live in headers in order for the compiler to be able to generate actual classes and actual functions from our blueprints. It has to have the blueprints available, so we have to put them in our header files. Yeah?
Wouldn't that lead to problems when you include the header files in several source files in your project?
That's a good point. So, in case it didn't come out, so could this lead to a problem when you include these things in several different implementation files? And the answer is no, it doesn't cause a problem. And the reason for that is because, first of all, as I said, class templates only lead to actual code when you instantiate. So, but let's say you standard vector is a good example of a class template. Let's say source file A has a vector of int, and source file B has a vector of int. So the compiler has taken the standard vector class template and it's instantiated the version for ints over here in file A, and it's instantiated the version for ints over here in file B. What happens is that in the last stage of compilation, the last stage of generating the executable, the linker comes along and it links together all our object files. This was something we talked about in classes way back, months ago. But what the linker does is it looks and it sees, okay, well I've got these two class definitions, or actually member function definitions, that are identical. They were generated from the same template. Right, these are, the technical terms, they're weak symbols. And so what it does is it just throws away all but one of the definitions. So yes, the source files will have multiple definitions of the same generated functions, but at link time, all but one of those definitions are thrown away. So another way of thinking about it, if you want to, is that the functions generated from templates are implicitly inline. It's the same effect that the inline keyword has. So if you remember if you write inline member functions, in headers, you have to put the inline keyword in there to prevent this problem of multiple definitions. And that's exactly the same problem. So template, code generated from templates is implicitly inline. And again, it's these weak symbols that the linker throws away almost all the work itself. So yeah, it's a very good question. And it would be a problem, but they thought about it and they came up with a solution. The other thing to say actually is this first point. So we instantiate a template with a particular set of arguments, and let's say for a class template, let's say for a function template, we instantiate particular template arguments. The compiler takes a template and it generates a function from that for those particular types that we've given it. Right, so let's say we've got a function template and we say we want to instantiate a version of this function to operate on ints. Now the compiler knows everything there is to know about ints. So it generates this function specifically, a version of this function specifically for ints, and then it can optimize the hell out of this function because it knows everything about the types that you're going to use with it. Again, this is why templates are quite different from generics in other languages, is that because we're generating new versions of these functions, we get the full weight of optimizations going in to the functions we generate. So this is another thing that makes these templates really fast because, as I say, there's no sort of type erasure going on. The compiler knows the types that it's using, it knows everything about them, it knows their size, it knows their alignment, it knows everything about them. So it can optimize really heavily. So it's another important thing to note. That's one of the things that makes templates so fast. So I've already mentioned class templates and function templates. What kinds of templates can we have? What entities in the C++ the language speak? What entities may be templated? Well, we can have function templates and we can have class templates, and these have been in C++ forever. C++ 11 gave us alias templates. So if you're familiar with type defs in C and C++ 98, C++ 11 gave us type aliases. So instead of having to do type def A, B, and the arguments the wrong way around, we can instead say using B equals A. It's much nicer. Or we can actually make these aliases templates as well, which is actually really handy. And it's something you can't do with type defs, and that's why you should, or one of the reasons you should just prefer using aliases whenever you can. C++ 14 gave us another new feature, that's variable templates. So this is something that doesn't get used all that much, But it's a neat little facility, and you can sometimes use it to avoid having to have a instantiate full class, which can sometimes be quite expensive in compile time. Variable templates are often work a little bit faster. So yeah, as I say, not something that gets heavily used, but variables are, you can have variable templates.
What do you mean by variables?
Actually, I specifically mean global variables in this case. So, yes.
Would that be predefined by the user anyway, what variables they use? So how would you create a variable very quickly and can be answered?
Well, why would you create a variable template? So, you almost never want to have a mutable variable template because you never want to use mutable global variables. But you can have constants. And one of the things you might want to do is define a constant pi, let's say. But you can have a variable template. You can define pi as a variable template. And then you can have a pi of type double, and a pi of type float, and a pi of type long double. Probably doesn't make any sense to do integer pi, right? If you're from Kansas and you want it to be 3, but so you can have that sort of extra type safety. Because if you use the mpi macro, then that's just a literal, so you're going to get conversion to double because that's what literals, floating point literals do, or whatever. But in C++ 14, you could use a variable template to define, pi angle brackets float. That would be it. Floating point constant equal to 3.14, whatever. So that would be, yeah. And in fact, C++ 20, we're going to have exactly that. We're going to have a pi constant and e, lots of other mathematical constants that are variable templates.
Would you have a pi string or a pi chart?
Not standard. Oh well, perhaps you could, but you probably don't want to. That's probably something you want to generate at runtime, as in if you need it.
Yeah, these are the kinds of entities that may be templated, but today we're mostly going to be talking about class templates. Actually, let me have a couple of examples of function templates as well. But yeah, the first two function templates and class templates are the most common. Alias templates are used quite a bit in C++ 11. Variable templates used more rarely. Okay, so how do we actually use templates? Well, actually, certainly everyone in this room has already used templates a few times, quite a few times. So there's already been a canonical example of a variable template, of a class template in C++. Will be standard vector. Everyone's familiar with standard vector. I think I get people who use it in the very first class, or if not the first, then certainly the second. So, as you know, standard vector takes a template parameter, which is the type that we want this vector to hold. Actually, maybe you don't know, but standard vector actually takes two template parameters. The second one is the allocator to use. That tells the underlying implementation how it should allocate memory. But most of the time, we just happen with defaults. So most of the time, we don't care about that. But we supply when we instantiate a vector, we create a vector, we tell it the type that we want to store in that vector. We give it the template argument. So everyone clear on the difference between arguments and parameters? Again, this is one of these things, and I do it as well, although I try and be careful when I'm doing these things, but we tend to mix up the terms arguments and parameters. And it's something that's defined differently in different languages, but for C sort of derived languages, we tend to refer to parameters are when you write out your, let's forget about templates for a moment, when you write out your function definition, when you write out a function declaration, the parameters of the function are the A, the B, the things that go in the brackets. Those are the parameters. Yeah.
I guess it's just a matter of perspective. what you expect as a parameter, what you provide as an argument.
Yes, what you expect as a parameter, what you provide as an argument. That's an excellent way of putting it. Yeah, absolutely. Yeah. So parameters are the things the function, the names of the variables that the function works on. The arguments are the things you supply when you call the function. And for templates, it's the same. We have template parameters, the things, the names we use when we are writing out our template, and then when we instantiate this template, when we tell the compiler to go and generate a bunch of code from this blueprint we've given it, we supply template arguments. And we write the template arguments in angle brackets like this. So here we've got a standard vector, and we say in angle brackets we want a standard vector of its. In this case, we want to use 1, 2, and 3. So again, this is something that you would have seen in perhaps class 1 or 2. Right? This is not world changing. But just want to sort of get the terminology. So here, int is a template argument that we're supplying to the standard vector class template, and the compiler sees this and it says, okay, I'm going to take this vector blueprint and I'm going to create a specialization of that for ints. I'm going to instantiate this and create from this template, I'm going to create a real class that is standard vector of int. And as I said on the last slide, because the compiler has all the information available about ints, or strings, or floats, or whatever type you're instantiating this with, it can really, really heavily optimize all of these member functions. And it allows unparalleled performance, really. And it's another important thing to note about templates that, again, makes them different to generics in some other languages, is that each of these generated classes is a distinct class, is a distinct new class. So if we create, as we have in this example, a standard vector of ints, this is a class. Standard vector of int is a new class generated from the vector template. If we were somewhere else in our code to have a standard vector of float, that is a second distinct class that is distinct from standard vector of int.
So you would in effect pass the parameter in for those angle braces.
Pass the argument in, yes. So the int here is a template argument. Yeah. Standard vector of int and standard vector of float are different types. Standard vector of string would be a third different type. They're not the same thing. So again, just something important to kind of have in the back of your mind when you're using templates.
A 2D vector is a template inside a template.
A 2D vector, so if you had a standard vector of standard vectors of ints, yes. So what you're doing there is that the compiler's going to, let's say you have a standard vector of standard vector of int. Well, first of all, the compiler's going to see the inner standard vector of int. It's going to say, okay, I'm going to generate specialization of the vector template. I'm going to use my cookie cutter to create a version of this just for ints. And then it's going to look at the outer definition. It's going to say, okay, I'm going to use my cookie cutter again, and this time I'm going to cut a cookie that's standard vector of standard vector of int.
So you can do the same thing with your own user-defined templates as well.
You can do the same thing with your own user-defined templates. Yes, you can. Yeah, absolutely. Yes.
What the outer vector would effectively hold is anyway just a pointer and allocator.
Vector, typical implementation of vector holds 3 pointers and then allocated it. Yes, you're essentially right. Yes.
Well, the data is somewhere else.
Yeah. So function templates, it's much the same story. So again, good example of a simple function template in the standard library is standard min. So it takes one template parameter, takes one template argument, if you want to think of it. And it just does, if A is less than B, return A, otherwise return B. So that's what it does. So, as with class templates, we can explicitly supply the template parameter, template argument right here. So in this case, I've created two ints, 3 and 4, and then I'm using this function standard min of int A and B. So standard min is a function template. We're saying, compiler, I want you to go and take this function template and stamp out, create a function from this blueprint that is specialized for ints. And that's exactly what's going to happen when you write the template parameter in here. We write the template argument, in here.
You don't have to do that.
But with function templates, you don't have to do that, no. Function templates allow us to do what's called template argument deduction. So again, you will have used this any time you've used the standard library, probably. For function templates, we're allowed to just write this. So this standard min here is where we look like we're just calling the function templates. What's actually happening here, behind the scenes, is that the compiler is looking at the types of A and B and saying, okay, well, A and B are both ints, so I'm going to deduce that the template parameter for my cookie cutter should be an int, because these things are both ints. So it's using deduction. It's deducing the type of T, because T is colloquially always what we use for unknown, for template, type template parameters. Saying, okay, I'm going to take T to be int. So it's important to sort of realize when you're looking at this, that we're not calling the function template, really. What we're doing is saying, hey compiler, please go and generate a function for me based on this min template. And I want you to just deduce the arguments automatically. And actually the way that the deduction works, and I might go into it a bit more next week, depending on how much time we have. The way the deduction works is exactly the same as happens for auto. So when you say auto I equals 3, that deduces I to be an int. And it's actually the other way around, because template deduction was first. So it's probably better to say auto uses the same deduction mechanism, the same deduction rules as templates do. So if you sort of got your head around how auto works, you can get your head around how template argument deduction works. The other thing that can happen is, in particular with standard min, let's say, because these things both need to be the same type, if I gave it an int and a float, it wouldn't be very happy, because it expects these things to be the same type. Here they are the same type, so it knows that it can just deduce the template parameter to be int. But if A was an int and B was a float, it would complain. It would be a compiler. It would say, I've got ambiguous deduction here. I don't know, deduction failure is usually how compilers term it. It's saying, okay, I don't know how to deduce, I've got conflicting information here. Do you want it to be an int or do you want it to be a float?
So would that be a compile time error?
That would be a compile time error, yes. So again, you have all been doing this for a little while, and this is probably already quite familiar doing this with all the standard algorithms. I've got you to use several of the standard algorithms in exercises and stuff. This is what's going on under the surface. When we use one of the standard algorithms, usually we'll pass iterators to them. Standard means it's a little bit simpler because you can pass the types directly, but most of the standard algorithms, they take iterators, and we don't want to have to write, standard : 5, angle brackets, standard : vector, angle brackets, colon const iterator. That would be horrible. So we use, let's say, standard define, and we pass it the iterator, we pass it the begin and end iterators, and the compiler then goes and deduces the correct iterator type and produces a specialization of defined function, defined algorithm for our iterator types. Everything up to this bullet point is C++ 98, in fact, way before C++ 98. C++ 17 added this new facility called class template argument deduction, which, if you hang around right to the end, there's a sort of take-home exercise that you can play with class template argument deduction. It's known as CTAD because, well, everything needs a name, and we like naming things in C++. But what this effectively allows you to do is go back. Oh, no, go back one more, please. No, that's too far. I give up. So what CTAD, class template argument deduction, what it allows us to do is we can effectively just omit this thing in here, and the compiler would just look at this. If we just said standard vector vec123, it would look at this initializer list, and it would be able to deduce that the class template argument that we want is int. There are a couple of differences between the way class template argument deduction works and function template argument deduction works, which is annoying.
So that's the back end.
Sorry?
Those things are more relevant for the back end than either the something you mentioned.
Why do I mention them? I mention them because they're C++ 17 and people do use them. It's not all that common yet, but I guess it will be as more C++ 17 code gets written. So if you see, say, just that standard vector without the template arguments in there, that's legal in C++ 17 and will deduce the argument to be int.
But would you recommend that as best practice? Because I remember just as like back to the beginning, you said it's good practice to be explicit in the argument. I mean, not in templates, but generally.
So my sort of general advice at this point, because I haven't used class template argument deduction that much yet. So my advice at this today would probably be to be explicit with your class template arguments. So I prefer to write this rather than that. Other people who are more forward-looking might say, well, letting the compiler deduce it is that's the future and that's the way we'll do things 5 years from now, so you may as well start doing it today. Personally, I would probably still write the type in, but other people might have different advice.
Let's see if we can get back to where we were.
So it's also a question of context. If it's a simple, it's easy to follow code. Whether where you're using it. If you're using a load of floats somewhere, a double somewhere, an int somewhere, and they all come together, then obviously it's going to be a problem potentially. If you're using a load of ints somewhere, doubles, floats, all in the same bit of code, then debugging potentially could become a lot more complicated if you just assume that the compiler's going to type.
Not necessarily debugging, because the debugger will always tell you the exact type of things, but the sort of golden rule that I think is you want to make it clear to the next person who's reading the code, sort of 6 months from now, a year from now, or 10 years from now. It's one of the things a bit like auto. If it's really clear from the context what's happening, then it's fine. Otherwise, probably err on the side, for me anyway, err on the side of caution and prefer to be explicit. So as you're using templates, we did that in 2 slides because I feel like you've all actually, probably without realising it, have used templates quite a bit already. You've used standard vector a lot if you've been following our classes. You would have used function templates in the shape of standard library algorithms. You might not have realised that you can explicitly supply the arguments, but you can. In fact, for function templates, you can supply some arguments and if there are multiple points, you can supply some and let the compiler figure out the rest. What you might not have done so much of is writing your own templates, declaring your own templates, writing templates. So how do we go and do that? Well, the first thing we do, for anything else, it's come out, is we use the templates keyword. This is the very first thing that appears. We use the template keyword, and then we write the template parameters between some angle brackets, like so. Template, angle brackets, type name T. And then we write the function signature. We're writing a function template. So this is a declaration of a function template called myFunction. It takes one template parameter, named T, and then one function parameter, which is a named argument and has type T. And similarly, if we're writing a class template, again, we start off template, type name T. T is really commonly used as a sort of, placeholder name for something that represents a type. Doesn't want to work for me, the clicker, never mind. So here is a class template. Intriguingly named my class. It's almost clearly lacking in inspiration in the RFPs. So this is a function template or a declaration of a function template. This is the definition of a class template. So here, in both of these examples, T is a template parameter and refers to a type name, to the name of the type, as you see in the type name keyword here. So we can name this thing whatever we like, but as I say, T is really common as a sort of placeholder. And within the definitions of these things, within the definition of the myFunction function template, and within the definition of the myClass class template, we can use the name T as if it were referred to a real type. So within the definition of myFunction, we could have a local variable of type T. Within the definition of myClass, we could have a member variable of type T. And what happens is that when we instantiate our templates, so these are the cookie cutters, and then when we come along and we actually create our cookie from it, the compiler, or think of it as blueprints, when the compiler builds something from our blueprints, it will perform what's called type substitution. So everywhere within the definition of my class, everywhere that if we had a member variable of type T, it would do type substitution, and it would substitute, if you created a myClass angle brackets int, it would create a member variable of type int. So T, within these templates, T represents as a placeholder for one of our, what will be our supplied template argument. So is it clear what T represents?
Yes.
Yeah? You're all on there with us? It can be any letter or any word or anything that would be a legal C++ name you can use. It's sort of convention to use T when we have a single type. If you have multiple, you might use T, U, and V. It's very common. You almost always give them initial capital letters, not all caps, but initial capital letters, just so within the body of this thing, you can see that it represents a placeholder type. Placeholder, not a real type, I should say. Yes.
So would you need to keep on in comma type name, or can you just have a comma T, A, B, T?
Good question. I probably should have, yes, you're right. I should have expanded the example. So if you have multiple template parameters, you do type name T, comma, type name U, comma, type name V. Why do you need to do that? Well, it's because C++ is actually kind of unusual. Yet another difference between C++ templates and generics in other languages is that C++ actually has 3 kinds of template parameters. Overwhelmingly the most common, what you just saw on the previous slide, what we call type template parameters. So we have a placeholder, conventionally T, that stands for a type. So we will instantiate our template with a given type. The user will supply a type. So standard vector, for example, has a type template parameter we supply. We also have things called non-type template parameters. So in this case, you supply a value. It's weird. And there are very strong restrictions on what types of non-type parameters, if that makes sense, you can use. Basically, up till C++ 20, they can be things that are int-like. So ints, enums, pointers, and that's about it. C++ 20 will vastly expand what you can use as non-type template parameters, but we won't worry about that yet. I'll leave it back.
Does somebody want to have a go at saying what a non-type template parameter could be? If you understood it, just pick something.
Well, there is a class, standard library class you've probably all used that takes a non-type template parameter.
It's just invent one. Might be going to declare. Why not?
Well, I guess the class that you're talking about is stood array.
Yes.
It takes not just a generic, but a specific.
Even simpler. If it were really simple, it's really simple when you can use non-type template parameter. Int, char, bool. Is that a template? That's a non-type template parameter.
Yeah. So basically, the things you can use in C++, up to C++ 20 anyway, are things that are int-like. So yes, bools, chars, ints, pointers.
Why wouldn't you just use a type template?
Why? Well, think of standard array as a great example. So standard array, you give it 2 template arguments, the type that you want an array of, and the size of that array. So the size is the compile time constant. It's a non-type template parameter of its type size t, just a big integer. So you supply the type that you want, the type template parameter, and a non-type template parameter, which is the size. There is a third type of template parameter, and if you are really good at using them, you should probably be out here teaching this because they make my head hurt. I have used them from time to time, but I always have to think very carefully about what I'm doing. They're very rare. There's something called template parameters. Yeah, they're not. Yes. Yes. Template parameters allow you to supply a template name as a template argument, and yes, if that sounds crazy to you, it is, basically. So this is the beginning and end of everything we're going to say about template parameters in this little module, right? They exist. They're weird and hard, but you know you can do some fancy things if you're so inclined. So by far the most common kind of template parameters that we use are type template parameters. They're the ones you're probably used to. But non-type template parameters turn up sometimes. Standard array, really good example, because we want the array size to be a compile time constant. And these template parameters, which are basically just used so people can show off how good they are at C++. You may have already seen this, but actually, when we declare a type template parameter, so on the previous slide, you saw I said template angle brackets type name T. We can actually use either the class or type name word there, keyword. So I could say template angle brackets class T. And that's a historical thing, basically, because templates in C++ predates the type name keyword. And so it's there basically for backwards compatibility. When I say template class T, it means exactly the same thing as if I'd said template type name T. The meaning is identical. And the type that you pass is not restricted to class types. So int is not a class type, but even if your template says template class T, you can still instantiate it with an int. Right, so using class as to introduce a template parameter is in some sense misleading because it sort of implies that you can only use class types. In fact, there's no such restriction. And so I'd recommend using the type name keyword rather than the class keyword. The class keyword is basically allowable there for backwards compatibility. So again, if you see it and you're curious about why it's there, it just means exactly the same thing as type name when you see it in a template parameter list.
What about struct?
You cannot, fortunately, you cannot say template angle brackets struct T. That's not allowed. At least.
But you can say class and use the struct. Use a struct.
You can say class and you can pass a struct type, yes, absolutely. You can do that. And in fact, in C++ 20, it probably will become legal to say template struct T, but it won't mean the same thing as class, and that's another reason to avoid using the word class. Yeah, C++ 20 is going to confuse this slide a lot, but we don't have to worry about that for another year. So let's have a look at a very slightly more in-depth example of a class, how we define a class template. So again, we start off with this line that says, what follows is a template. It's a template that takes one argument, it expects a type name, I've used T. Again, just to name the point, I could say template class T here, and that would mean exactly the same thing. So this is a class template. We use the keyword struct. That doesn't matter. Struct and class are the same thing. Yes?
I have a question. It's a bit arbitrary. I'm totally nothing to do with email writing. What year did you do C++?
What year is it now?
19.
14?
13, 14, something like that. So, I've got my class template wrapper, and first thing we're defining is a constructor, and our constructor takes a single parameter of type reference to const T. Again, T is the placeholder for whatever the argument to our class template is. And the constructor just does exactly what you think it does.
Why is there an underscore before the
Well, what does this line do? Anybody tell me?
Initiate.
Sorry?
Initializing.
Yeah, so this initializes something, member variable named value underscore with this thing value. So in a minute you're going to see the member
Oh, you
value.
need as a variable, like the sort of type.
type name a value. Now that would be confusing. So we've got another member function called getValue. Const member function returns const tref, returns yet to be defined member variable named value, a corresponding set value. And finally our member variable down there. So this is our blueprint for how to create a wrapper. Saying, when you create a wrapper, I want you to, when you create this class for a particular type, I want you to create a constructor that takes const tref, whatever t may be. I want you to create two member functions, one called getValue that is const qualified, and one called setValue that takes the new value. We'll just do the assignment. So again, if this was not a template, then I just replaced all these t's with ints, and hopefully everybody will be able to see what was going on with this example. So here I'm creating an instance of wrapper. I'm instantiating the wrapper class template with a float type. So what this does is the compiler goes and looks at our blueprint, looks at this blueprint, performs type substitution. So everywhere that it sees t, it substitutes in float. So we're going to have a wrapper that takes a wrapper constructor that takes const float ref. We're going to have a getValue member function that returns const float ref. We're going to have a setValue function that takes another const float ref. And it's going to have a private member variable type float. And then having created this instance, we're going to declare a const because, you know, that's just good practice. And because we've now taken our template and we've generated a real class from it, we can, of course, call the member variable, call the member function, just as you'd expect. So we can print out getValue, which is going to print out 3.14. We can create another instance, another instantiation of our wrapper template, this time specialized for ints. So again, the compiler is going to go away, it's going to take our cookie cutter, and it's going to stamp out another cookie for ints this time. So it's going to generate the constructor, it's going to generate the member functions, it's going to generate the member variable. So here's a question. If I call wf.setValue with a float, does this compile or not?
WF. Oh no, it's const.
Oh, sorry, that should say WI. Let me just quickly change that. It should, well, it certainly would with WF. It should say WI because that's a more interesting question.
The first question to ask is, what type is it going to expect in set value?
Yes.
I think I would probably narrow it down to it.
So this is, you're absolutely right, yes. This is going to compile just fine. So what's going to happen here is WI, we have chosen our type parameter when we created this instantiation. So it's performed the type substitution, it's decided that t is, or not decided, we've told it that t is int. So it's performed the type substitution,
And so it's generated a member function called setValue, whose parameter type is const_int_ref. And so when we call setValue on WI, the argument type that it is expecting is const_int_ref. That is, this doesn't do any type deduction at all, right? Because there's no type deduction to happen because we've already explicitly told it what type we want to use. So we've now got, it's got a const_int_ref parameter. We're trying to supply it with a float. Is that going to work? Yes, it is. Perhaps it shouldn't, but it is going to work. It's going to truncate our float, in this case to 1. But yes, it will compile. It will work just fine. So it might be absolutely right. But the point of sort of asking this question is to sort of, perhaps there was no confusion. Perhaps that's what you all expected to happen. But this doesn't lead to any sort of type deduction going on here because we've already stamped out this class with it. It's already decided what the argument type to set val is.
With 1.99, it just slides on 0.99.
I think it always does truncations. Floating point to integer conversion, yes. Right. It's been a nice lot of chatting from me, hasn't it? It's the first time I've done this in months. I've forgotten how to do this. Anyway, there's been a nice lot of chatting. But I think what's even better is if I get you lot to do some typing. So this is the first of several exercises today. So if you, I think Laurent's the only person who's been coming here long enough to have done this before, because this is a reuse exercise. But I think only Laurent would have done this a couple of years ago. But if you go to github.com/super+/templates exercises, you can go to that repository, you can clone it onto your machine, as you all know how to do because you've all attended our GitHub classes. Clone that onto your machine, you'll see there are, I think, 5 different exercises in the README. I would like you to have a go, please, at exercise 1. So I've defined this int pair class for you. I want you to turn this into a class template for holding 2 different types, or possibly different types anyway.
If you need help as usual, just shout.
Absolutely.
It's always on that. It's dying. So, since there's nothing back there, I'll leave it here. Can you mute that mic, Simon? Is that it? No, it's that one, isn't it? No? No. The power one is the power mic.
Yes.
Magical. Is it feeding into the Mac?
No.
Okay.
Just from the room.
Okay.
So it actually has the
It should be. So what you do pair, so it's calling the constant plus type pair up here. So pair could be any type. It's a class. So it needs a we don't know what it is. Can't because there's no, so here, it could be anything. It's got to be template. So the read. Okay. But we have to put pair inside the brackets. Find something out. Pair expects two types. We don't know the types. And then we just put in type.
Now, where do we get to the new frame?
Well, from our
You get on okay?
well, we haven't put it in yet. We don't know.
So what we need to do is we need to make it.
This one.
Oh, okay.
No, this one.
Okay,
So
no, we don't need that, do we?
Yeah, we're still doing that.
Okay.
So now what this is saying is the print pair is a function takes two to the input.
Yeah. Yeah.
And if someone supplies us with a pair,
Of whatever.
a specialization pair, we're going to be able to deduce with T.
Okay.
This is the correct solution to this.
Right. So if I should work then.
So now there's part one C.
Maybe test your pair.
It's very important. Still meant to be. So well, in fact, it only works now because we're using science percentages. Well, this only compiles correctly because you have to use science percentages. So you're using 14, this would be 11.
Oh, really?
Yeah. You know what?
Because we haven't defined.
We haven't told us, we haven't told, yeah, exactly, we haven't told pair. So at the moment, this is using that C tag.
Okay. So here, we want to do that.
No, not that. Lovely, it's the template on, sorry, fine. So, it's a pair. And then hold bracket.
Oh, and
This is almost like, it's very nice and it's smoother and nicer. But then there's that blueness to it. It's almost like this blue cheese. Almost like a gold. But then after we said that the blue is like more blue cheesy. Quite tiny, quite tiny.
Okay.
Yeah.
So pair, there's a pair, ins, pair, double.
Should use real.
But I have something else.
Sneaker stuff.
Sneaky stuff.
Yeah. Just explain.
I just figure out you don't have to apply that to so the independent permit is but I thought it said
Personally, just find it courtesy. The person who's signing it doesn't seem to not sign it because I think
He does this half the people.
not how it works.
Oh, right, so yeah, I'd like to use, there's a really good blog post by Chris Koloff, who's the guy who does Easy. That I read, probably 4 years ago. Explained exactly how to use. No, that's.
No, that's not Chris.
Oh no, hang on. He references these things. Yeah. So that was what taught me how to use. The other person who uses it a lot, is a guy called Noel Douglas. But yes, there's
well, it's but I don't know. Right. Although I have to say, I was looking at with arrow. But it's actually there.
well, no, you're done for part one. You're going to have a go at part two very, very shortly.
But frankly, I was thinking about, have you worked with
not a lot, a little bit.
Because the singleton question is like using the singleton just because you can compare if something belongs to
Yeah, I remember getting a bit confused on the difference in their code and their category. It's a long time since I used it, so I saw the question, I thought, I code that voice.
You know,
you can buy.
are you familiar with market trends or with market categories?
Not very much.
Who's completed it? Or these are these ones. You see them on there?
Yeah, fine. How you doing? Someone? Excellent. Yeah, well, you know, you guys are the pros. You've been coming to these for ages. You just blast through all my little exercises now. Well, that is still quite satisfying from my point of view because it means we've done a decent job. But all the solutions to these exercises are on the GitHub. So there's a solutions, EX1, etc. branches. You can have a look. So if we just have a quick look at the pair header. So first of all, for this class pair, started off holding 2 ints. I wanted you to change it to a class template that held 2 arbitrary types. So it's pretty much the same as that example that I showed with the wrapper type, except this time we've got 2 template parameters, called them T and U. You can call them anything you like, but T and U is common. Got our constructor, so we've just changed int and int into T and U, get first and get second, and then const overloads as well. And we changed it so that we have 2 member variables of types T and U. The slightly tricky bit perhaps was that you have to do a corresponding thing to this print pair free function. So previously we had a function called print pair that printed a pair of ints. Now we want to change it to a generic function that prints a pair of any kind. So the way we can do that is to just have this function void print pair, and the argument type that it expects is pair of something, some T and some U. And we can write this as a generic function, like so, and then when we call this function, not a function, it's a function template, when we instruct the compiler to instantiate this function template, by providing a P, it will deduce what T and U are from the pair that we supply it with. So we can have a look in main, and we see we create a pair of ints, and we can just call print pair P, and that will deduce T to be int and U to be int. In the second case, it will deduce T to be double, U to be double, and in the third case, T to be standard string and U to be int. So, when we remember that we can write member functions of classes, we can define them inline in our class, nice and easy. And we can also write them separately, define them outside our class. And when we do that, we have to use this sort of abstract form, say a return type, say the
a member function name and its arguments, and then we use this like class name : colon. So this is the member name that belongs to this class name. So again, we've all been coming to these things for a while. You know how to define these other class member functions by now. We can also define member functions of class templates using the same sort of basic formulation, but we have to tell it what the template parameters are that we're going to use. So we have to use this template header, template introducer line again, template type name t, type name u, and now we say return type class template of t and u, and then our member function name and its arguments, and then the implementation. So just like we can for normal member functions of classes, we can write member functions of class templates separately from the definition of the class. However, they still have to go in header files, because this is part of the blueprint for the class. The compiler needs all the blueprints available to be able to generate all the right functions. So, although you can write this separately, it still has to go in the header file. It still can be useful to do, just to keep the class template definition quite small and clean, because especially for templates, this might be a really long function, so you might just want to put it somewhere way down in the header file, so it's easier to read. But this code still has to belong in a header file. So it's not like when we have just normal classes where we would typically put this in an implementation file. Class templates, because they're blueprints, we still need to have the blueprints available in order to generate a function class from it. But, yes. So,
will it still define multiple versions of the member, even if it's not depending on the template? Even if the member doesn't call any of the template parameters, will it still create instantiate one version for each instance of the template?
basically, yes. Essentially, yes.
Become like you separated the definition from the declaration.
Yes, that's exactly what we're talking about.
So you have a templated definition in isolated translation.
No, I'm saying it has to be on the header.
The definition needs to be in the header, or are you going to go into the exception to the rule?
No.
Okay. There is an exception to the rule.
What is the exception, Ollie?
The exception is when you know exactly what types you're going to want. So you can split that definition off, and then in the translation unit of the definition, you can explicitly instantiate all of the types you're going to commit, and if anybody tries to use something other than those types, it's all compiled, spell stick, it still won't build. As long as they use the types that you ordain, it will link because they will be instantiated. It's also useful as optimizations. You can split the definition template out, you have a known set of types you want to allow, just give you some operating speed up.
So yes, it's possible to split the declaration of a member function of a class template, separate the declaration from the definition, and if you want to do that, then when you come to write the definition, you need to say this. You need to say the template, class template name, followed by its template arguments, and then colon member name. And exercise 2, if you've already looked ahead to do it, was to basically do this for the get first and get second members of the pair. But I'm not going to get you to do that now. You can do it at your leisure. I think you guys are probably well on top of that. But if you want to have a go at it, be my guest. But we've only got half an hour left, so I'm going to go on to talk about explicit specializations. So this is really template specialization is one of the things that makes C++ templates as powerful as they are. One of the things actually, interestingly, that makes them Turing complete
which was a sort of accidental discovery. It wasn't designed in. People afterwards realised that the C++ template system was so powerful it was actually Turing complete, which is crazy. It's crazy. But let's not worry about Turing completeness just yet. Computing things at compile time. Let's just worry about what specializations are. So we have our template, we have our generic blueprints. Sometimes it may be the case that when we instantiate our template with a particular type, we want some special behavior. So an example might be if we've got a function template. Well, we know if you are using an int with this function template, we can have a specialized version that uses like SIMD instructions like SSE and all the other, specialized instruction sets. Perhaps we have a generic template that can operate on any type, but if you supply us with a particular set of types, or you supply us with an int or an unsigned or something that we know all about, we can use these intrinsics to make things faster. So in this case, we want to be able to define a specialization of the template for a particular type.
Can you think of it as template overload?
It's almost template overloading, but not quite. Another example. Another example. Say we've got some class template that's under the hood holds an array of some values. We might think it's a really good idea that if somebody instantiates our template with a bool, well, you can actually store an array of bools really efficiently by just storing the individual bits. This probably seemed like a really, really good idea in about 1995. Turned out to be a really bad idea. But this is actually, for those who don't know, this is what standard vector does. There's a special version of standard vector just for bools, and it's actually not very good. But it's an example of how we can use, or of what specializations can do. So specializations say when we can supply a special definition that is used when we have our types, when we have a particular type. So in that case, we'll say, right, I don't want you to use this generic blueprint, I want you to use this special one that I've said just for jokes. Yes. So we've got our wrapper class again, a couple of slides ago. And this is our generic class template once again. This is what we call the primary templates. So now we want to define a specialization just for ints. And to do that, we first of all need to use this curious syntax. We need to say template and then this empty angle brackets. And this is like a marker that says to the compiler, I am about to give you an explicit specialization. And now for our specialization of wrapper for ints, we're going to do something a bit different. So this first line, template empty argument list, says this is an explicit specialization. And now we have struct wrapper again, but now we're saying this is a version specially for ints. And I'm missing my opening curly brace, but imagine it's there. Might start. Go and write it in because I don't like the look of it. So now, just as we did before, we're going to create an instantiation of wrapper for floats. And this is going to use the primary templates, as you would expect. But now, this time, when we do what we did before and we create a wrapper events, this time the compiler is going to look and it's going to say, okay, well, you've told me to create a version of wrapper for ints. Oh, but you've also told me there's a special version of wrapper just for ints, so I'm going to use that. So it's going to use this version. So this uses the specialization of this just for ints. So we can say wi.value equals 8, let's say. So here's a question, what if I call wi.getValue? What's going to happen?
I'm guessing it won't compile.
John's guess is it won't compile. John is absolutely right. Because this guy down here has no member function called getValue. Right? The primary template has a function called getValue, but the specialization does not. And this is actually something, I'll say about it again in a second, but it's actually something that's very important, is that specializations don't have to have the same members, the same member functions, the same interface as the primary template does. You can do, well, pretty much anything you like in a specialization. It's completely, as far as the compiler is concerned at least, completely unrelated. The contents of it is completely unrelated to this guy up here. You could have completely different implementation, completely different members. As we see here, we've omitted the member functions, we've omitted the constructor. We happen to have a member variable called value, but we can give this a completely different name if we wanted to. It's a separate class.
Once you've templated wrapper, you have to template everything else.
Once you've
You couldn't just do struct wrapper. You need to template close brackets.
Yes, you need this line to say, to tell the compiler what follows is a template specialization, explicit specialization. And it's called an explicit specialization because when we say wrapper float, that's telling the compiler to generate a version of wrapper for floats. That's an implicit specialization. That's the compiler is specializing this template for type float. So when we say wrapper float, it's going to use the primary template. That's an implicit specialization, a specialization the compiler is generating. But here, we said wrapper is an explicit specialization. That's where the name comes from.
Explicit is when you, the programmer, did it. Implicit is when the compiler done it for you.
Exactly.
If you find value as a float and then cast it as an int
Where? Oh.
in your code, so if you say wrapper or 3.14, then you
If I said wrapper,
WI is a float.
yeah.
WF was a float, and then you cast it to 3, static cast or something.
That's not gonna. It's not. No. This is going to decide which specialization to use, depending on by which argument you give it here. Okay. And CTAD, by the way, I know we're not really talking about it, but CTAD only considers the primary template. It doesn't bother about specializations. Doesn't know anything about specializations. So, in talked earlier about which kind of entities may be templated. Class templates, function templates, variable templates may all have explicit, otherwise known as full specializations. We'll see in a second why they're called full specializations. Here's a line that I might expect might cause a little head scratching. But explicit specialization is not a template. So I said to you at the beginning, it's really important to get your head around what the difference is between a class and a class template, right? The cookie cutter and the cookie. Not the same thing. We use one to generate the other. So we use the templates to generate the specialization. We have our wrapper blueprint, our wrapper cookie cutter, and we use that to create a cookie for floats, let's say. But now we're explicitly specializing. Explicitly telling the compiler, okay, when you, in a particular case that the template argument is nibs, I don't want you to use the cookie cutter, I want you to use this other thing that I've defined.
Is that a part of?
So, actually, wrapper, brackets, angle brackets, int, is a class. It is not a class template.
You're overriding the
Yes, yes. In the same way that when you say wrapper, angle brackets, float, that is a class that is generated from the primary template. Wrapper event is a class, but it's not generated from the primary template. It's generated, or it is the thing that you have said that it is. It is.
Isn't it inside the template itself? The template is passing the argument to that specialization.
I can see where you're coming from, but no. No, it's bypassing the whole cookie cutter mechanism.
Is what I meant.
Yeah. So these things may be specialized, class templates, function templates, and variable templates may be specialized. However, you do not want, or you should not generally specialize function templates. It's usually considered a bad idea. It is allowed, it is permitted, it's not a great idea to do it. And the reason is because functions, as well as having this specialization mechanism, also, well, one of the reasons anyway, is that as well as being able to specialize, you also have function overloading, and the there is a set of function overloading rules that are really complicated, a set of specialization rules that are a bit complicated, and the two interact in sort of strange and unpredictable ways. And it is sometimes not entirely clear whether you're calling a function overload, whether you're going to get a specialization of a template. It's all a bit weird and mysterious. And the advice from the gurus on high, people who know C++ a lot better than me, say do not specialize function templates.
Right, do you not specialize what?
Function templates.
Oh, function template.
Do not specialize. No, class templates. Go ahead.
Okay.
Do not specialize function templates. Use overloading instead. And as I said on the previous slide, the actual implementation, that is the interface, the member variables, the member functions, member types, if you've got member types, the compiler, it doesn't enforce anything. You can have a completely different class interface in a specialization to what you have in the primary template.
I'm just going to expand on the function template thing. I do agree that it's mainly a bad idea. A lot of the reason for it being a bad idea is that it turns into a massive flirt gun, as in you shoot yourself.
Next slide. Wait one slide and then interject. So this is one of these many, many cases in C++ that you can do something clever. And I feel like a lot of the time I've spent at the front of these classes is saying, yes, you can do something clever, but you probably shouldn't, right? In fact, yeah, it's one of these things, C++ gives you just enough rope to shoot yourself in the foot or whatever the thing is, right? You just as you can make
operator equals fire missiles, but you probably shouldn't. You should probably make operator equals do what people expect an overloaded operator to do. And this is a similar case to that. If you're going to have a specialization of a class template, make it obey the same interface, the same rules as the primary template does. Don't surprise people. And this is why this vector of bool specialization is universally hated, is because it makes a vector of bool behave differently to how a vector of any other type does. Right? The idea of using a compressed representation for bits is not a bad one, but the implementation, but it means that vector of bool behaves differently to a vector of any other type, and that sucks. So unless you are doing special clever tricks, and there's this thing called Sphene that I want to talk about next week, but ensure that the specialization, if you need to write one, that it has the same interface as the primary template does. Don't surprise people. Another one of these cases where just because C++ lets you do something clever doesn't mean that you should do something clever. So this is probably not surprising. We know this already because we know that we have to declare things before we use them in C++. That's, again, something we covered many moons ago. But in order to declare an explicit specialization of a template, the compiler needs to know that that name represents a template. And this is the second reason why it is a bad idea to specialize function templates. Because of this complex relationship with overloading, that it means that actually, if you're particularly mischievous about it, you can actually change the meaning of C++ programs with function template specializations. Just by reordering the declarations can give you a different meaning of your program, which is horrible and crazy and madness, and you shouldn't do it. And that's another reason why you should avoid specializing function templates. And my main reason for putting this on the slide is because it leads into what is my absolute favorite quote from the C++ standard, which, I really wouldn't recommend reading it in its entirety. It's like 1,200 pages of boringness. But they managed to sneak in past the ISO, this body that defines all these international standards. They managed to sneak in a limerick. When writing a specialization, be careful about its location, or to make it compile will be such a trial as to kindle its self-revelation. Yes, I mean, I don't know who it was who managed to get a limerick into the C++ standard, but I love that it's there. And yes, this is basically telling you, this only really applies to function templates, specializations. So, yes, I love that there's a limerick in the standards. We've got 9.5 minutes. At this point, I was going to give you. Sorry. Let's party. Well, you can party by doing. This is. Yes. All right. Let's do this. Because I was going to go on to talk about partial specializations, but rather than rushing it into 9.5 minutes, perhaps I'll spend a little longer on that next week. So perhaps instead, I'll get you to practice with your explicit specializations and turn your textbooks, please, to exercise 3 of this same thing you did. You can have a go at exercise 2 as well if you want. Exercise 2 I don't think will be too problematic for you guys. But exercise 3 asks you to write a specialization of the pair template. I believe I said it's for 2 minutes. But yeah, if you have a go at that, and it's a little bit of practice of writing a class template specialization. And that way, we won't have to rush the remaining little bit of the lecture into the 9 minutes that we have available.
So extra control, the green on something, extra control, extra control. I'm told that it's very nice. I think that's the code. You have it, it's cheap. That's the code. So, I think extra control to go to, engage. Extra control, engage. Yes, the red one is what she said. So I think you should have the red one first, that's the mark. And we'll do it with these. You should start with red, then you should have the black, then you should have the green. All things. They help stop these tracks. When you go on websites, it says, so you have your DDoS attacks. Well, Jesus is. There's a blue. Which one are you on now? But what about the test? Have you not had the test?
Specialised parts. So, what does it have to do? No. So that's the first bit. Then you need to talk either what you're going to specialise. So after the word tear,
There is a typo in the reading. I'm very sorry.
you tell it what you're going to specialise.
It needs comma two. Apologies.
That should, so if I've got standard array,
It takes to argument. Template type takes to argument. So the array is a template.
Class template.
So the first argument is the type. And the second argument is number of elements. Yeah, you did. Yeah,
so
yeah.
so that should work. And I just need
No, you need to, if you want to do
T equals
you can give it an initializer list now.
that should work.
Yeah.
Yes, an initializer list. That works fine. This is instantiation. You can leave it array.
We're getting there in the end. It's like
Yeah.
typos and like, right,
Does it
okay,
have
where's
to?
my red? No. What's wrong with that? Why can't?
Oh, no, you can't construct it like that. That's the record.
I have to do it.
You have to do code braces. You have to just do do it as arguments. It's, no, you don't have to do that.
Doesn't that work?
I mean, it would. That's it, right? It would. Well, we need to do an assignment, but don't do that. That's the theory. That's what we need. It's not harder. P. So you want to construct an initialized next year, so you have P.
Yeah.
So
It's
it's first layer like
First layer of curly braces.
That's the usual.
The constructor.
Yeah.
And the second layer is initialized.
The entire standard library basically is templates.
They're like a very common tool.
Yeah, there are downsides to using templates as well.
P, I have actually easy sent to T.
Because I want to tell you they're great. There are downsides
Oh,
to
sorry.
using templates as well.
You're replacing them.
So then your function and your organization.
Oh, okay. I remember that. There's always,
Yeah.
Unless it's in here, I would really.
I don't think you can specialise in
It's curly brackets below.
So this is redundant because it's an array. It's not array.
Depends.
It's an array's default constructor. It's not zero initialized, does it?
Value initializing as well.
You could do what you say.
Like if you
could do that.
use an array into curly braces, nothing inside the curly braces.
Zeros.
It does zero.
So you do that.
So I think there you go.
Okay, that's okay. I didn't know that.
Yeah,
That's
that's
interesting.
just fluff default. That's actually you don't have a default.
All these are all
pointers.
Okay. You're still holding it into the first and second.
Oh yeah, sorry, you want to move the array down.
To the private part.
Place that. Now you need to fill in for the fetch function.
Yeah, no, that's as far as I've got. Well, I need print pair. Yeah, that was the one that
So
question.
just print pair? You still need an accessor, even with print pair, because that's private, which it should be. You should leave it private. There's no way to do that using that, right?
Okay.
So the original, if you go to the original pair,
So it's 9 o'clock and probably time to wrap up.
You've got to get to them.
But just-
You need to get to them.
Just before we go, perhaps something that could be considered a trailer for next week. Do you want a trailer for next week? Yeah.
Go on.
Okay.
Get first and get second.
Oops. How about this?
Yeah.
Compile time Fibonacci sequence. Yeah. So one of the exercises I want you to do, again way back when, was to write a function that computed the Fibonacci sequence. So that's each term of the sequence is the sum of the previous two terms. So I mentioned that C++ templates, when you with specializations are Turing complete. This was actually something that was discovered. I'll tell them I'll say this next week again, but it's something that was discovered accidentally. But one of the things it lets you do, for example, is to compute Fibonacci sequence at compile time. And this is what we're doing. So this static assert, this compile time assertion, we're asserting that the sixth Fibonacci number is 13. And this is purely compile time. Right? Absolutely no runtime. Absolutely zero runtime code is generated from this. This is pretty cool. So there we go. Next week we'll go into doing things like this. A bit of template meta programming. We'll go into it a bit more. But that's it for today. Thank you. A few of you for coming. It was a bit of a funny session tonight, but thanks for bearing with us. Thank you everybody who's been following online. Tom, are you going to...
Thanks very much for Christian. The reason we are in so small numbers is because there are gaps. Yes, gaps between availability, wonderful weather, and so on. Obviously, that does not help. That does not help with. That does not help with the with attendance. Now, the next week we are in the same place here, and obviously we will dive in further into templates.
where here is Cloudflare, I suppose.
Yeah. So in the Cloudflare offices.
Near the Millennium Wheel.
Yes.
London Eye.
London Eye,
Sorry, London
or
Eye.
Coca-Cola, or whatever the name is, whoever is the current owner. After this class, we are going to pub and obviously
your input to make sure these two guys will look after is appreciated. Can you ensure that the space is spotless clean? We need to put the power cord and so on safely back so they can. So Cloudflare will be happy to host us next week and hopefully in the future. And that's all from me. See you next week. Thank you very much.